Alright, so I just wanted to make a little video to try to go through Chapter 6 pretty quickly here. So Chapter 6 in my notes, and also in Gamelin, is on Laurent series and isolated singularities. Less on how to calculate, more on existence, really, here. So a little bit on the history, just to start with. Laurent was a French engineer. He lived 1813 to 1854. It seems like Cauchy wasn't too impressed to start with. The extension of Laurent seems to us worthy of note. Well, apparently so. We're still talking about it.
Hi.
Anyway, so Laurent's proof, actually on Laurent series development, is found in a publication by his widow, published in his honor, 1863. But you know, as the years went on in the 19th century, I think everybody became aware of this. There's more on the history, as usual, in Ramir. I would encourage you to read there if you're interested. All right, so let me go on here. First order of business is that we're introducing this notation. F is an element of, holomorphic at z naught. Holomorphic at z naught, let's say, means that there's some open disk on which the function's holomorphic. All right. In other words, it's complex differentiable on some open disk. Now we got started there. Okay, so what is the Laurent decomposition? Well, the Laurent decomposition here, we're going to look at an annulus, all right? So annulus has some inner radius rho, some outer radius possible sigma. They could be 0, they could be infinity. In other words, it could be a disk. It could be a so-called exterior domain. So, we want to have our cake and eat it too. These annuli, they can be inside out or they can be outside in. In the sense that you have disks that include all the center, or you have, the outside of a disk. Both of these things are possible annulus in degenerate case, but we consider those. Anyway, so the Laurent decomposition simply says this, that if you have a function which is analytic on some annulus, then you can decompose the function into two pieces, the analytic piece and, let's say, I'm not sure what the good name is for these. Maybe you could call this the interior analytics piece. This is the exterior analytic piece. They're both analytic, but in different places. This one's analytic within, this is analytic without. In the sense that, for less than sigma, for greater than rho. Okay, so just a few examples. First of all, z cubed plus z plus 1 over z. Well, that breaks into this polynomial plus 1 over z. This z squared plus 1, of course, is, and so the annulus, the annulus in consideration here is the punctured plane unioned with infinity. So we consider the extended complex plane as we look at this section. It's helpful to include the point infinity or to exclude it as to make the conversation more explicit. Now, this z squared plus 1, of course, is analytic at 0, whereas 1 over z is not analytic at 0. On the other hand, z squared plus 1 is not analytic at infinity, but 1 over z is. So again, interior analytic, exterior analytic. F naught is z squared plus 1, F1 is 1 over z. Great. These standard examples, exponential, sine, sig, cosh, are all interior analytic, but not, they're all just, the whole thing is interior analytic. So the exterior piece is 0, so it's kind of a special case, right? Let's see here. So example 6.14. If f of z is analytic infinity, that means there exists some exterior domain for which f of z is analytic. All right. In that case, you can identify that the f naught piece is 0. So this is the 6.13 and 6.14 are kind of mirrored examples, inside out, let's say. They're inside out of one another. The proof here, then, of the Laurent decomposition theorem consists in two parts. The first part we prove is uniqueness. If we have two Laurent decompositions, all right, say f naught plus f1 and then g naught plus g1, then if you look at their difference, right, let's see here, where is it, what did I do? Right, two Laurent decompositions. Of course, f of z is equal to f of z, so this is equal to that, right? But on the overlap, right? So now these are two Laurent decompositions with respect to the same annulus, right? So the same inside and outside domains. The inside domain both have G naught and F naught. The outside domain have G1 and F1. So you could calculate this H of Z to be the difference of the two pieces in the inside or the outside domain. And with that, we have that H of Z is entire, right? And not just that, but it goes to 0 as Z goes to infinity. So what do you got? Well, you've got a bounded entire function. So you can apply Liouville's theorem and conclude that H of Z is constant, right? But in particular, if we look at the points within the annulus, right, where H of Z is actually defined, we have, because in the on the inside, so you notice that the let's see here, well, we have the H of Z is equal to 0 inside the annulus because there we have both Laurent decompositions, right? Excuse me. So there we go. H of Z is equal to 0 at one point, but then H of Z is constant, so it's 0 everywhere. And then we get the uniqueness of the Laurent decomposition. Okay, so the let's see here. The existence then is from Cauchy's integral formula, as we talked about. Basically, we just take a point in the annulus, let's say Z, between and so the R and S here is basically giving us a subannulus of the annulus. So the rho is inside here, and the sigma is in principle outside here. Of course, rho could be 0 and sigma could be infinity, but the idea remains the same. And so you pick out the subannulus, and then on that subannulus you have a it's not simply connected, but it's a domain, right? And there's one hole in it, so we can apply Cauchy's integral. We can apply the Cauchy's integral formula with a hole in it, which basically says that you integrate counterclockwise around the outside of the domain, and you subtract the counterclockwise oriented inside of the domain as you apply the formula, just like Green's theorem with holes in Calc 3. And so when you do that for some point Z in this annulus, you get the following. You get the integral of f of w over w minus c dw, or over the s, right? The plus 1, because that's the outside. Counterclockwise, I'm getting clockwise, yeah, counterclockwise, right, like this. So 1 over 2 by I, of course, this is Cauchy's integral formula. And then on the inside, again, counterclockwise, and, over equal to r in there, f of w dw. And we then argue that this is f naught of z and this is f1 of z. Well, how is that? Well, excuse me. Excuse me. Well, it's nothing terribly profound. Here, S is the outside, right? So if you just look at this and just apply Cauchy's, essentially just Cauchy's integral formula for the disk, excuse me. Well, I guess you don't get, not the disk, but here to there we get, words. So this is going to be analytic from S back to R, right, by the construction of the theorem. Whereas this piece over here, of course, will be analytic. This is going to be analytic from R out to S. All right, so I think I must have that this is analytic. Right. Oh, sorry. Let's turn the page here. I think there's something I'm forgetting. Notice F naught is. Make sure I'm in frame here. There we go. Notice F naught is analytic for. Let's see here. I'm trying to get this both in the. So notice that F naught is analytic for z minus z naught less than s, and f1 is analytic for z minus z naught greater than r. And f1 of z goes to 0 as z goes to infinity. As z goes to infinity, that doesn't make sense. I think that's supposed to be, that should be r, I believe. Well, I think there's some details missing in this proof, honestly. I'm going to go on here. My time is limited today. But anyway, I think the uniqueness argument is fairly clear. And again, it's just Cauchy's integral formula. All right, so anyway, I think page 347 of Vermeer is probably superior to what I'm doing at the moment. Anyway, that said, let's go on here. So here's an example. This has this partial fractions decomposition 1 over z plus 1 over z minus I. And so on the annulus 0 to 1, you have that the piece which is analytic inside the before good grief, modulus of z less than 1, this is analytic, right? Modulus of z greater than 1 over modulus of z greater than 0 rather, we have f1 is analytic, right? So I think the thing that's tripping me up is I keep forgetting that we have the Laurent decomposition on an annulus, right? But the f0 and the f1 they're actually analytic beyond the annulus, right? Like f0 is analytic to the middle of the annulus, whereas f1 is analytic from the inside edge of the annulus all the way out, and that's the thing that keeps getting me. So like, sorry, I'm gonna go back here one more time. So this, of course, if we're if you just look at this disk, right? F is what? What do we assume about F here? We assume F is analytic in the annulus, right? I still don't see why it's got to. I'm worried because we don't know anything about F in here. How do I get this formula make sense even though we're going all the way down there? I guess the point is that whatever evil's happening in here, it's accounted for by that piece. But I think the proof of that is missing in my notes at the moment. So some guy running around my neighborhood with a flag, apparently a pirate flag. Pirate flag exercising. Well, that is different. All right, moving on. True story. All right, see here. So where was I? All right, so another example, sine z. Basically, the Laurent decomposition, you can look at annuli which fit between the successive zeros of sine z, right? In other words, between n pi and n plus 1 pi. For example, if you look at n equal to 0, we have sine of z is this, right? So we can use geometric series to calculate the reciprocal by factoring out a z. And we get like that, right? So essentially we have the principal part, which is, I'm talking about principal parts, but we'll define that soon enough. The principal part's 1 over z, and here's the polynomial piece. So this is the f1, there's the f naught, of course, plus dot 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 dot. On the punctured disk of radius pi centered at 0, there's the Laurent decomposition. All right, so anyway, moving along. Suppose that, where was I? There we go. Suppose f of z equal to f naught plus f1 of z is Laurent decomposition for some annulus. Then we have two things going on here. On the one hand, because f naught is analytic and the inside, right, we have that the Taylor's expansion applies, and f naught of z sum k equals 0 to a sub k, c minus c naught of k. On the other hand, f1 is analytic on the outside of the exterior disk of radius rho. And so then we get this, sum of reciprocal powers, as we discussed back in the analytic functions at infinity discussion. So this is f naught, this is f1, but when you put them together, you've just got to sum over all integer powers of the power function z minus c naught to the k. And more than that, we have normal convergence of this piece, we have normal convergence of that piece, and the annulus, of course. We have both of those things. And so we get normal convergence on any subannulus, all right? So we can define a function f of z defined by the Laurent series centered at z naught by k equals minus infinity to infinity of a sub k times z minus z naught to the k. Let's call this star, all right? The question then, of course, is what are these coefficients? What's their significance? Now, before we'd have just said it's just a evaluation at the of the derivatives, right? Because we only had the positive powers. But now we've got a little bit more. So we wish to characterize the meaning of the coefficients. I'll start out with just the simple case of a sub 1. So, well, I didn't know that, but we just integrate f, right? Plug in the series Laurent series decomposition. And then compute the, take the sum outside the integral by the uniform convergence. And then of the inside and the outside piece. And inside the annulus we have both. And this breaks down to 2 pi I Kronecker delta of k minus 1. That's the only non-trivial integral here. And so we get 2 pi I a to the minus 1. Apparently this integral has the significance of being 2 pi I times the minus 1 coefficient in the Laurent series. But I think the other way to look at it is, if we can calculate the Laurent series, then we've calculated this integral, which is pretty cool. In fact, that is the trick we exploit to great efficiency in the next chapter. All right, now, so here's an example. Make sure I'm in frame again. All right, so sine of z over 1 minus z. So what am I doing here? Looks like I'm expanding around z minus 1. So I think I'm doing something on the punctured disk at 1. And so usual add 0 trick. You get this thing. So here's the principal part as it's known, and then here's this analytic inside, analytic outside, right? And so a minus 1 is sine of 1. So if you want to integrate the sine of z over 1 minus z over, say, the disk of radius 2, centered at 1, I mean circle of radius 2, not disk, I'm an idiot, circle of radius 2, centered at 1, then it's just 2 pi I times sine of 1 by what we just did. Wow, man, that's pretty cool. Anyway, so continuing our derivation to figure out the rest of the coefficients in the star expression that we talked about a minute ago, if we integrate f of z over z minus z naught to the n plus 1, then again we can plug in the Laurent series for f of z, but if we divide by that it shifts the power function a bit, and then again pull the summation out. Then we integrate this, but the integral of this power function is only non-trivial when this whole thing is the net minus 1 power. So Kronecker delta k minus n minus 1 comma minus 1. But of course the only way this can be, these match is if k is equal to n. So we just have the summation from minus infinity to infinity collapse down to one term, 2 pi I a sub n. Now, I think it's probably important to notice that I can't, generally speaking, tell you that, I mean, if we have analytic in the center point of the annulus, right? If z naught's the center of the annulus we're looking at, then we can calculate the nth derivative at z naught and divide by n factorial, and that will be equal to this, right? But these examples we're looking at, that may not necessarily be the case, because we might not even have that the function is analytic at z naught, and yet this integral can still be calculated and account for whatever sort of bad behavior the function has at z naught, let's say, all right? And that all gets lumped into the exterior piece in my view. All right, so anyway, to summarize what has happened so far, we have this Laurent series decomposition theorem. For 0 less than equal to rho, less than equal to sigma, less than equal to infinity, if we have that the function's analytic on this annulus centered at z naught, then we can decompose f into a Laurent series like so, where the coefficients are given by these integrals. Simple as that. And also there's no, we can figure out there's no hidden dependence on the radius chosen here, because we have the deformation theorem. We can adjust the r. We can look at different subannuli and we'll get the same coefficients, even though we have slightly different circles. So there's no artificial dependence on this r if you think about it. All right. So the next section is on isolated singularities of an analytic function. I'll talk through these results too. They're pretty simple. So it's isolated singularity if the singularity is isolated. In other words, if there's a punctured disk that you can look at where that's the only singularity. So we have three kinds. There are three kinds of isolated singularities. You've got yourself the removable singularity. You have the pole of order n, and you have the essential singularity. Removable means that the Laurent series is actually a Taylor series, I would say. There's no reciprocal terms. It's a pole of order n if you have some reciprocal terms, but not too many. Finitely many reciprocal terms, right? Finitely many negative powers of the power functions e minus c naught to the k. And it's an essential singularity if there are infinitely many reciprocal terms. Riemann's theorem on removable singularity simply states the following. It states that if z naught is an isolated singularity of f of z, if f of z is bounded near z naught, then f of z is a removable singularity. The proof is very simple. The proof says that if you take the Laurent series in a punctured disk like so, if f of z is bounded, all right, this, I don't know what this is. Anyway, there's a typo in my notes here, I think. Anyway, so the modulus of a sub n, right, is equal to the modulus of this integral. We just derived that the formula for a sub n is this integral. But by the ML estimate theorem, this is less than or equal to the bound for this integrand. But the bound for this integrand is given by m. The length of the integration curve is 2 pi r. And then we divide by, what, 2 pi, and then this 2 pi r to the n plus 1, right? Because that's not a... This is actually, modulus this is actually equal to r to the n plus 1. There's no kind of... the only inequality going in here is the bound. All right, everything else is equality. Well, the ML theorem, I guess, the L is also an inequality, but anyway, whatever. So this gets you m over r to the n. Now, as r goes to 0, right? Excuse me. As r goes to 0, you notice that a sub n is going to go to 0 for n less than 0. Why is that? Well, if n is less than 0, right, this is really like m times r to a positive power. And of course, like, you know, m divided by, for example, r to the minus 2 is really mr squared, right? Mr squared goes to 0 as r goes to 0. So basically, all the negative coefficients here have this going to 0 as r goes to 0. And consequently, we get, and since, but r is arbitrary, right? We can make r as small as we like. You know, we can make r as close to 0 as we want. We can consider this limit as r goes to 0. It's reasonable. And so it then follows that all of the negative coefficients are 0. And so we're just left with the rest of it, which is a Taylor series, you know, a polynomial without end, if you like, centered at z naught. For example, sine of z over z, right? Sine of z over z, take the power series for sine, divide by z, you get this. Once you bring in that, the odd power drops to an even power, and you get this. So, as you can see, there's no reciprocal term. And you can simply define f of 0 to be 1. This is removing the singularity, right? Now, anyway, so again, I've been using this terminology already, but if we have a pole of order n, this piece, the piece with reciprocal terms, is called the principal part. If n equals 1, it's a simple pole. If n equals 2, it's called a double pole. All right, great. So the theorem that we have is very useful. We keep using this again and again in what follows. Let z naught be an isolated singularity of f. If z naught's a pole of order n, it's a pole of order n rather, if and only if f of z is equal to g of z divided by z minus z naught to the n. So this has all of the, let's say, badness encapsulated in it. The g is actually an analytic function at z naught, all right? So the proof is actually very simple. Suppose the f has a pole of order n, right? So by definition, its Laurent series look like this. Then you can just factor out a 1 over z minus z naught to the n piece. What you're left with here then is something which begins at the 0 power once you reindex it, right? But then this is just an analytic function at z naught, and consequently, and also its constant coefficient is a sub minus n, which is not equal to 0 by assumption. Therefore, you have it, f of z is equal to analytic function divided by z minus z naught to the n is claimed. That's the one direction. Conversely, if there is g which is analytic with g of z not equal to 0, and f of z is equal to that, right? Then that means you can find coefficients for the series expansion of the g, and then if you just do the calculation, and divide that into that, then bam, you've got a Laurent series that starts at minus n, and so again it's a pole of order n, just as we claimed. So it's if and only if. Now, that doesn't seem like much, but when you actually apply it to examples, it's actually very meaningful. For example, e to the z over z minus 1 to the fifth, e to the z analytic at c, hence by theorem, f has a pole of order n equals to 5 at z not equal to 1. Done. This one, there's a typo in my current notes. Like, this is supposed to be, this was supposed to be the third power, and this was supposed to be the fifth power. If you look at that, I made that adjustment in everything that follows. All right, so like 1 over z minus 1 over z plus 2 to the fifth power times the power series for the sine of z plus 2 cubed. So z plus 2 cubed to go z plus 2 cubed, 1/3, z plus 2 cubed cubed, which is to the ninth, and so forth. So when you clear out, when you reduce the powers, remove, let's say, the singularities that you can. Anyway, cancel like factors, I'm not saying. You end up with z plus 2 to the squared out front, and then this. This, of course, is analytic at minus 2, and so there you go. Function has a pole of order n equals to 2 at minus 2. This theorem is also useful. If z naught's an isolated singularity f, then z naught is a pole of f of order n, if and only if 1 over f is analytic at z naught with a 0 of order n. So there's this interplay between poles of order n and zeros of order n for the reciprocal function. Very natural. And the proof is very, very simple here. It really just uses the thing we just proved. If you have a pole of order n, then you can write f is equal to g of z divided by z minus z naught to the n. So if you look at 1 over f, right, then this, it flips over, right, and then you've got z minus z naught to the n times 1 over g. But, of course, 1 over g is analytic, if g is analytic, and if g of z naught is not equal to 0, then 1 over g naught is not equal to 0. And so by the characterization of zeros of order n, this shows that 1 over f has a 0 of order n. And then conversely, if you have 1 over f as a 0 of order n, then you got this, and then you flip it over, and then bam, you've got f is g of z over z minus z naught to the n, which again shows that f has a pole of order n, given that g has a 0 of order n. All right, so there's this, assuming 1 over f has a 0 of order n. It's very, very simple, very simple. Nothing too hard to understand there. So, but despite the simplicity of the proof, it's actually a very powerful result because, for example, 1 over z has a simple pole at n pi. Since you can just look at this, sine of z is sine of z minus n pi plus n pi. So by the adding angles formula for sine, you get cosine n pi, sine of z minus n pi, and then the other term plus sine of n pi, which is 0. So the other term goes away, and we just left with that term from the adding angles formula for sine. And then if I expand this into its power series centered about n pi, I get this, right? And so you can see that, in fact, we have a simple 0, because the first term is linear, right? And I can factor out that, and then I've got, anyway, it's clear that it has a simple 0 from this, and consequently 1 over sine has a simple pole. I would encourage you to study the example on 173 and 174 of Gamelin. That example's got a little bit more to it. Good reading. There's some very simple thinking basically here. You look at this, so it's got like a pole of order 3 at 0, and it's got a pole of order 6 at 2 plus 3i, and then that's just how it works, all right? Now, this definition is important to be with us for a while. We say a function f is meromorphic on a domain D if it's analytic on D except at possibly isolated at singularities, each of which is a pole. So in other words, meromorphic means it's analytic most everywhere except where it's not, and where it's not, it's just a pole, all right? So every entire function is meromorphic on C, but an entire function does not have to be analytic at infinity, right? Sine of z is entire, but it's not analytic at infinity. So, for example, sine of z would not be meromorphic on the extended complex plane. In fact, rational functions are meromorphic on the extended complex plane because every rational function can be written as a polynomial plus a proper rational function. The polynomial of order n is a isolated zero at infinity of order n, and then the rational piece is going to be analytic on the complex plane with isolated zeros wherever there's a zero in the denominator function. That's it. So this theorem here, z naught be an isolated singularity of f, then z naught's polar of order n if and only if the modulus of f of z goes to infinity as z goes to z naught. Now I said something wrong in class the first time. I said that the isolated and the essential singularities both have a modulus which blows up to infinity as you approach the singular point. That's not true. It's only true for the pole of order n. For the essential singularity, there's a different behavior, which we'll talk about next. Anyway, so here it is. If it's a pole of order n, you have this formula, right? G of z divided by z minus z naught. So if you look at that, then you have, f of z is this, but g of z is, analytic, so hence it's bounded. So you can get that by m, then you have z minus z naught to the n, to the minus n. And, but here n is a positive thing, so as z goes to z naught, and the modulus of this goes to infinity, because that's like, division by a small positive number, right? When you look at the modulus. I'm missing a modulus here, I think. Okay. So there you have it. The converse direction, of course, if you have the modulus going to infinity, then that means that there's some r, all right, such that f of z is not equal to 0. Let me take a drink here. So of course, if f of z goes to infinity, it means that there's values which are not 0, right, on any punctured disk like this. But if these are, and it can't be 0 if you get sufficiently close to z naught. Of course it can't be 0 if this is going to infinity, right? Because if this is going to infinity, that means that if you get close enough to z naught, all of the values of f of z have moduli which are larger than whatever value you like to pick. So certainly they're not 0. But that means that 1 over f of z is analytic on that same annulus. But then that f of z goes to infinity as z goes to z naught implies that this h of z goes to 0 because it's the reciprocal. But then that means that h of z is bounded near z naught, and that means by Riemann's removable singularity theorem, you can write it as a power series like that. And then you can extend then h of z to be 0 at z naught. So finally then if the 0 has order n, then h of z is z minus z naught to the n times b of z, where b is holomorphic at z naught and b of z naught is not equal to 0. So you obtain that f of z is equal to just what you want. It's got a 0 of order n. All right. Sorry, my cold is catching back up with me again. I'm gonna try to wrap this up before I say something stupid. This is an essential singularity because you have infinitely many reciprocal terms at n, right? With respect to 0, of course, right? And you can see that the behavior, it's not, you don't have that the modulus of this is going to infinity as z goes to 0, because while it is true that there are certain rays or directions which go to infinity, like this, x equals to, if you approach on the positive x-axis, right? Positive real axis, it blows up to infinity whenever x goes to infinity. But if you study the approach on the imaginary axis, you have that the modulus is 1 all the way to the the modulus stays 1. So if the modulus of f of z is blowing up to infinity, you can't have it approaching to be 1 from one direction and approaching it to be infinity the other direction. You need infinity from all possible directions to get infinite modulus, right? That's the thing I was forgetting. Duh. And that, of course, is tied to this Causarati-Weierstrass theorem that says that if z naught's an an essential singularity of f of z, then for every complex number w naught, there is a sequence zn goes to z naught such that f of zn goes to w naught as n goes to infinity. In other words, essential singularities are really weird. They basically, it's like this is your life for the complex plane. Every single value that the complex plane takes on is approached at least by an essential singularity close to the point. And so here's the proof. It's more of the same. I'll let you read it. And I'll pause there for a second so you can see it. Anyway, it's on page 135 of my Guide to Gamelin notes here. Then there's Picard's theorem, which, by the way, states that for an essential singularity z naught, there is a sequence zn goes to z naught for which f of zn is equal to w naught for each n, except for possibly one value. So like for e to the 1 over z, the one thing that you can't find sequences which are constant as you approach the z naught is 0. You can't get e to the 1 over z to be 0, but anything else you can find a sequence of points going to z naught for which e to the 1 over z is equal to 3 plus I, or natural log of the log of principal logarithm of 32 plus 7i. I mean, whatever. Finally, then, this section 6.3 is on isolated singularities at infinity. Basically, it's the same song and dance, but at infinity, everything is basically just fed through this reciprocal function idea. It's an isolated singular point in infinity if the reciprocal function g has an isolated singularity at w equal to 0, and likewise the pole of order n, the removable singularity, and the essential singularity are likewise defined. Now, the formula, of course, is a little bit different. At infinity, the principal part is the polynomial part, and the other piece, I don't know what we'll call it, so sort of the f0 and the f1, so to speak. They're flipped over. The principal part is the polynomial part now, and anyway, if you take the difference of f of z and the principal part, you get an analytic function at infinity. All right. Here's some examples. E to the z has an essential singularity at infinity. E to the z is meromorphic on C, but not on the extended complex plane, right? But again, like I was saying, any rational function, you can do long division and rewrite it as a sum of a polynomial plus a proper rational function where the degree of the denominator and the degree of the numerator are distinct, and in fact the denominator wins, right? It has a larger degree, let's say. So in this, the principal part is d of z, and this piece is analytic at infinity. In fact, so anyway, any rational function is meromorphic, is the bottom line there. If you have a proper rational function, the way you extend the function to infinity is just to find f of infinity to be the equal to the ratio of the leading terms. All right, so it's like every wrong thing a pre-calculus student ever did with limits at infinity has become a definition here. Well, the ones that we can make definitions at least anyway. And then here you go, e to the 1 over z minus 1 over z. You work this out, you get that. And so here the singularity at infinity is removable because the polynomial piece cancels out. And so you can extend f to be analytic on the extended complex plane by simply defining f infinity to be 0. Okay, so anyway, next time up we're talking about partial fractions, so I'll do that in class, I hope. Thanks. Bye.